The paradigm shift in robotic intelligence. For decades, roboticists have pursued two divergent paths: precision-engineered industrial arms capable of repetitive tasks with micrometer accuracy, and ambitious but fragile home assistants that struggle with basic chores. Physical Intelligence's PI 0.5 represents a fundamental breakthrough that bridges this divide. Unlike conventional architectures that funnel all decision-making through a central processor, this system distributes neural computation across the robot's entire body. The implications are profound. Machines that can enter completely unfamiliar environments like apartments or offices and perform complex manipulation tasks without pre-programmed maps or constant human oversight. This innovation transcends incremental hardware improvements. At its core, PI 0.5 reimagines how artificial systems perceive and interact with the physical world. By combining decentralized microintelligences with a sophisticated vision-language-action model, it achieves unprecedented adaptability while dramatically reducing power consumption. Early testing shows robots that can sort dishes, make beds, and tidy rooms in homes they've never encountered before. A capability that could transform industries from healthcare to logistics. The fatal flaws of centralized robotics. Traditional robotic systems suffer from an inherent architectural limitation. Like a medieval kingdom where all decisions must pass through a single monarch, they rely on a central processing unit that becomes both bottleneck and single point of failure. Every sensor reading, whether from a camera, torque sensor, or fingertip pressure pad, must travel to this central brain for processing. The computed response then makes the return journey to actuators and motors. This approach creates three critical vulnerabilities. First, latency accumulates at each step, making real-time adjustment impossible when handling delicate objects or navigating dynamic spaces. Second, the constant data shuttling consumes substantial energy, limiting operational duration. Third, any failure in the central processor paralyzes the entire system. These limitations explain why factory robots excel at repetitive welding but fail when asked to load a dishwasher in a home environment. A biological blueprint for machine intelligence, PI 0.5 S revolutionary approach takes inspiration from biological nervous systems. Just as human reflexes operate through spinal cord circuits without waiting for cortical deliberation, the system embeds autonomous neural nodes throughout the robotic body. The two-layer cognitive architecture, layer 1, the peripheral nervous system. The foundation comprises dozens of PI nodes, self-sufficient microcontrollers embedded in joints, grippers, and tactile surfaces. These nodes operate on an elegant reinforcement learning principle. After every micro-movement, each node evaluates whether the action improved its immediate objective, reducing slip, minimizing joint strain, and adjusts its neural weights accordingly. This continuous self-optimization occurs without central oversight, enabling remarkable adaptability. Hardware agnostic by design, these nodes can run on everything from inexpensive ESP32 chips to custom silicon. In one compelling demonstration, a soft robotic gripper equipped with PI nodes achieved 30% better manipulation accuracy while drawing 25% less power than conventional designs. The implications for mobile robotics are profound. Distributed intelligence could enable days of autonomous operation rather than hours. Layer 2, the central executive. While PI nodes handle reflexive control, higher cognition resides in a vision-language-action (VLA) model that understands commands, plans task sequences, and interprets complex environments. Trained on an unprecedented diversity of data, 400 hours of real home robot footage, cross-embodiment demonstrations, and web-scale visual language corpora, this model develops robust world understanding. The training methodology reveals why PI 0.5 generalizes so effectively. Unlike systems trained in sterile lab environments, it learned from robots navigating genuinely cluttered homes, dealing with shifted furniture, variable lighting, and unpredictable obstacles. Human instructors provided verbal coaching, creating naturalistic examples of task decomposition. First find all dishes, then separate silverware. This curriculum produces machines that understand both the physics of objects and the semantics of human spaces. Performance that redefines expectations. Rigorous testing across 100+ unfamiliar home environments yielded startling results. When given language commands like clean up the dining table, PI 0.5 achieved 94% task completion, matching the performance of systems that had specifically trained on those spaces. Ablation studies proved the necessity of diverse training. Removing multi-environment data caused performance to crater to 31%, while models without web-scale visual knowledge struggled with object recognition. The system's real-time operation showcases its biological inspiration. Every second it executes a cognitive loop.
Training thing, illustration of co-training tasks in this Pi 0.5 recipe, which includes robotic data sources, variety from many different robot types, as well as multi-model data that includes high-level subtasks, commands, instructions, and data from the web. So you have robot action data. So in the wild, mobile robot, in the wild static robot, office static, general robot data. You also have multimodal data like verbal instructions, close the microwave, subcommands like pick up the mitten, object detection, multimodal web data. So all this is used for training the
The VLA model generates textual reasoning, move the plate to the drying rack, converts this into 50 joint angle updates via flow matching, a rapid alternative to diffusion models, while PI nodes handle micro adjustments. This separation of timescales, deliberative planning at 1 Hz intervals with reflexive control at 1000 Hz, mirrors how human motor systems combine conscious intention with spinal reflex arcs toward a new generation of intelligent machines. Physical Intelligence's roadmap hints at even more transformative possibilities. Future iterations may incorporate self-supervised learning from real-world operation, allowing robots to improve continuously without human labeling. The team envisions models that ask clarifying questions when uncertain. Should I put the medicine bottles in the cabinet or on the nightstand? And transfer skills between radically different hardware platforms. Commercial applications are already emerging. Healthcare facilities could deploy PI-powered assistants that adapt to each patient's unique living space. Logistics robots might handle irregularly shaped parcels with human-like dexterity. Will distributed intelligence finally bring robots into our homes, not as clunky gadgets, but as truly helpful companions? PI 0.5 proves that the answer might be closer than we thought. From self-adjusting grippers to robots that understand messy reality, this isn't just an upgrade, it's a revolution. The ethical frontier of distributed robotics. As PI 0.5 blurs the line between machines and biological intelligence, it raises profound ethical questions we can't ignore. Should robots making autonomous decisions in homes have fail-safes beyond code? How do we prevent these distributed neural networks from developing unpredictable emergent behaviors? The system's ability to learn from real-world interactions means we'll need new frameworks for robot accountability, especially when they're handling fragile items or assisting vulnerable populations. Unlike conventional AI, where responsibility traces to centralized algorithms, PI 0.5's decentralized nature demands we rethink everything from liability laws to privacy protections for the sensory data constantly being processed throughout its body. The commercial revolution ahead, PI 0.5 architecture, solves two major barriers to commercial robotics: energy efficiency and real-world adaptability. Imagine warehouse robots that don't need meticulous programming for every new SKU, or hospital assistants that can navigate unpredictable human spaces without constant supervision. Early adopters in manufacturing are already seeing 40% fewer error-related stoppages during product changeovers. The technology could be particularly transformative for elder care, where robots need both delicate touch for assistance and robust understanding of cluttered living spaces. As the system moves toward commercialization, keep an eye on sectors like agriculture for delicate produce harvesting and disaster response, where environments are never predictable. What comes after PI 0.5? Physical Intelligence's roadmap hints at even more radical evolution. The next generation may feature quantum-inspired neural nodes for ultra-efficient computation or biohybrid systems incorporating organic sensors. Researchers are particularly excited about swarm applications, where multiple PI-enabled robots could share learned reflexes across a network, creating hive-mind adaptability. There's also work on emotional intelligence layers that read human microexpressions through distributed vision nodes. One tantalizing possibility? Robots that develop regional behavioral dialects based on their operating environments. A Tokyo-based unit might learn more meticulous cleaning patterns than its New York counterpart. The future isn't just about smarter robots, but machines that adapt to human culture as fluidly as they adjust their grip strength. Want more cutting-edge insights on AI and marketing? Visit judyfmarketing.com for deep dives into the innovations shaping tomorrow. What's the first chore you'd trust a PI 0.5 robot to handle in your home? Let me know in the comments. And if you enjoyed this breakdown, don't forget to like, subscribe, and hit the notification bell so you never miss an update. The age of intelligent machines is unfolding fast, and you won't want to miss what's coming next. Thanks for watching. Until next time, stay curious.